Okay, so let's continue on with 1.2, sets of real numbers. And it's going to be really important for these problems that you refer back to the diagram that was at the beginning of Module 1, Section 2, to make sure that you are familiar with what to do and how to classify numbers. But I'll give you a really brief overview. All the numbers that we're dealing with right now are real numbers. But real numbers split off into two groups. They're either going to be rational numbers or there'll be irrational numbers. Irrational numbers are numbers that when you take the square root of that number, it gives you a decimal. So numbers like the square root of 17, the negative square root of 8, the square root of 35, and numbers like that. Those will all be considered irrational numbers. Pi is also an irrational number because we know that that is 3.14 and it continues on and on and on. So you know irrational numbers never repeat and they never terminate. So the best way to know whether or not you're dealing with an irrational number is simply to take the square root of the number that you're questioning. And so if we want to see what the square root of 17 is 17, press square root, and you get 4.1231056, and it continues on and on. So this number is an irrational number. In the same way, the square root of 35, square root, you get 5.9160797, and it goes on and on and on. So you know that you're dealing with irrational numbers because, again, they never repeat and they never terminate. Even if the number is negative, it's still considered an irrational number if the decimal never repeats and never terminates. So if it is not an irrational, then it must be rational. Now within rational, there are subcategories. So a few examples of numbers that are just rationals would be things such as 12 over 4. Why? Because it's a fraction, and we know that 12 over 4 is going to be and actually let me give you a better example. 12 over 14 would be a rational number because it's written as a fraction, okay? But it doesn't classify as any other type of number because it's a decimal. When you divide 12 divided by 14, 12 over 14, you get a number that actually I'm going to not use that as an example because it is a rational number in that it does repeat, but on your calculator it won't look so clear. But let's use a different example. Say, for example, 3 over 4. When you take 3 over 4, you end up getting 0.75. And 0.75 is a terminating decimal. It stops after 5. And so you know that it's a rational. But numbers that are rational numbers but still have a greater qualification are integers. Integers are numbers like -2, +8, and I'll actually do all the negatives out here. -2, -8, -9 over 3, because that's really just -3. Those types of numbers will be integers because they are going to be numbers that are not decimals, so they are whole numbers as based on the current definition. But we're going to keep the negatives out here because inside integers, we're going to talk about whole numbers. And whole numbers are just the positive integers. So where there's a -2, there's a +2. Where there's a -3, there's a +3. Where there's a -8, there's a +8. And the thing that's critical about whole numbers is the number 0 is a whole number. And you can remember that because you can see here WHOLE, and there's a 0. It looks like 0 belongs in the word whole. And so you'll know that whole number is going to include 0. Where integers are positive or negative whole numbers by themselves are uniquely positive. So let's see how that applies to our example. We're asked to write all names that apply to each number. And so with the first example that we have is 121 over the square root of 121. In order to do this, all you have to do is simplify the number. Well, if you follow the order of operations, we can consider the radical sign like a grouping symbol. So the first thing you'd want to do is to find out what the square root of 121 is. Now, if you don't know, use your calculator, 121 square root, and you'll find out that the square root of 121 is really 11. So my denominator will now become 11. My numerator will stay 121. So this becomes a new problem now. So 121 divided by 11 is going to be 11. So my question is really, what names apply to 11? So if we go back to our diagram, you can see because the number 11 would fit in the whole number circle because it's positive and it's not a decimal, then you would know that this will qualify as a whole number. But because it is also a integer, it's a decimal, it's positive or negative, it would also classify as an integer. And everything that is an integer classifies as a rational. And everything that is a rational classifies as a real number, but it does not classify as an irrational. So you would therefore need to give the final answer that states that 11, or the 121 over the square root of 121, is a whole number, an integer, a rational number, and a real number. So all it is really knowing the definition of those terms. So if you study that chart and you know what examples look like, it'll be pretty easy. Number 9, on the other hand, is pi over 2. And one of the things you have to know is that pi is absolutely a irrational number. The number pi is actually written as 22 over 7, and when you divide that out, it becomes a number that does not repeat and does not start over. Let me just show you on the screen. If I was to calculate 22 over 7, I would get 3.142857142857143, and you would continue on, and we would consider this an irrational number. Now, because it's an irrational number, when you divide it by 2, and by the way, pi is not exactly 22 over 7, it's approximated because 22 over 7 by itself, because it's a fraction, is rational, but again, pi is one of those numbers that continues on forever and ever and ever, and it actually does not repeat and it does not terminate. So if you took that number and you divided it by 2, it's still going to be irrational. So there's no need to do anything else with it. There's not even a need to calculate it. Once you see a number that has pi with it, it's always going to be irrational. So number 10, tell whether the statement all integers are rational numbers is true or false. And so we've been talking about this throughout the review. So all integers are rational numbers. Is this true or false? Well, let's go back to the diagram. As you can see, integers, very simply, fall inside the realm of rational numbers. So no matter what integer I choose, if it's negative 1,000 or positive 100,000, they still fall in the rational category. So absolutely, all numbers that are integers are also rationals. So if I was to write this out, then I would simply say, yes, all integers are rational numbers. And the reason is, explain your choice, is because all whole numbers can be the product of division. So all whole numbers, because all integers, can be written as fractions. And I'll say expressed as fractions. So this is just a sample of what you might get. So the key is knowing the definition and being able to justify your answer based on the definitions that you know. So that's it for part 2. We'll continue with 1.3 in a second.